I hope I am audible and my screen is also visible.
Yes, sir.
Okay. So in the previous classes, I have discussed about the different kind of discretization formulas that we use. Can you please turn off your go from this side. Hmm. Now there is no echo. I hope. The screen got shared. So I hope there is no echo and the screen is also clearly visible. Uh, so can any one of you confirm?
So slide is not visible. Your voice is audible.
The voice is audible, but the screen is also visible. So I
No
will write
screen
on
is
it.
not visible. There is no slide is visible.
I hope the screen is visible. Others can open
Yes, the screen
Malik.
is visible, sir.
Screen is visible. So I think you can reconnect and then have a look at it. So previously in the class itself, we discussed about central difference formula, central difference discretization scheme. Okay. So for example, there is a heat conducting rod like this, a slab like this, which actually have a temperature of 100 to 500 degrees centigrade, or anyone like TA and dB. Okay, and then you take a control volume like this, an arbitrary control volume, where capital P is basically your center of the control volume, and this one is basically the control volume on the right hand side is capital E, which is the center of the control volume at the eastern part of the P control volume, and there is capital W, the centroid of the control volume at the western part of the P control volume. Okay, and these small e and small w are basically the cell faces, which is common between capital P and capital E. So small e is basically the common cell face between capital P and capital E, and small w is a common cell face between capital P and capital W. Okay, so that's how it works. So as discussed in the nomenclature that we have discussed. So for example, if I write the discretized equation itself, so it looks like gamma of d phi dx A. So this is the equation I'm getting after applying the Gauss divergence theorem on the general transport equation. So which people have seen in the previous classes. So gamma d phi dx multiplied by area W plus S bar delta V equal to 0. Okay. So therefore, what we will do is basically, so how it looks like is that, for example, the general transport equation is that general transport equation is gamma del square phi equal to plus source term. Okay, so this one is basically equal to 0 for a convection, for a diffusion plus source problem. For a diffusion plus source problem. Okay, so gamma of del dot grad phi plus s equal to 0. So what I do is basically I apply the Gauss divergence theorem, that is dV plus s dV equal to 0. Then we actually use a volume integral over it. And then what we do is basically we convert this volume integral into a surface integral by using the Gauss divergence theorem. So which is n cap dot grad of phi dA surface integral plus s delta V equal to 0. Okay, so gamma of this actually becomes gamma d phi dx multiplied by area small e minus of gamma d phi by dx capital A, which is A is basically the area of cross section, which is D is basically area is basically dy into dz or y in this one is a thing. So if I consider these to be uh, dz and this to be dy, this area. So this actually becomes a cross section of the rod itself, and then plus of base delta v equal to 0. Okay, so S delta V actually gives you the source term. So what I did was actually I took the general transport equation for the diffusion plus source term. Okay, so then what I did was actually I used a Gauss divergence theorem and converted that into uh, a simplified equation. And after that, we will use a central difference formula in order to express this gradient as a function of that of the neighborhood cell centroids. Okay, so this d phi dx will be expressed as a function of phi e, phi w, and phi p. So what we are doing is basically we are converting a partial differential equation into a set of algebraic equations. That's what we are doing. So is it clear to all of you what I'm doing? Hello, am I audible?
Yes, sir.
Okay. Then what we will do is basically we will use a central difference formula. So gamma a d phi dx east minus gamma a d phi dx west plus ace delta v equal to 0. Then gamma a. So for example, if I actually draw the control volume again, so this is capital P, this is capital E, and this is capital W. And this is small e and this is small w. So this is phi e minus phi p divided by delta x minus of gamma a phi p minus phi w divided by delta x plus of is delta v equal to 0. Okay. So this equation actually becomes gamma a by delta x and then 2 gamma a by delta x phi p equal to gamma a by delta x phi e plus gamma a by delta x phi w plus is delta v. Okay. So for an arbitrary control volume which is at the interior part, which is not at the boundary of the rectangular section that I've taken. So for that, by using the central difference thing, we can write this equation. Okay. So is it clear to all of you?
Yes, sir.
Yes,
Okay.
sir.
So then what we did was actually I also showed you that how to deal with the boundary nodes. So which I will show you again. So for example, if I take the boundary node like this, sorry, the boundary cell centroid. So if P is basically your boundary cell centroid and E is basically your P cell centroid. Okay. So Ka dt dx east minus of Ka dt dx west plus is delta V equal to 0. Okay. So east is basically this phase and west is this phase. So small w we already know. So T of small w is basically equal to T of A. So these are called the temperature at the boundary, which we also known as a boundary condition. So here the value of the temperature is given. So this is called the Dirichlet boundary condition. And so this one can be written as Ka uh, T2 minus T1. So if this one is 2 and this one is 1, since if I draw the cells like this 1, 2, 3, 4, 5. So T2 minus T1 divided by delta X minus of Ka T3, sorry, Ka. So this will be T1 minus Ta divided by delta X divided by 2 plus SdB equal to 0. Okay. So this is called the Fodor difference formula, and the first one is called the central difference. Okay. So this one is the order of delta X, and this one is the order of delta X square. Okay. So is it clear to all of you? So I have derived the expression for the Fodor difference formula previously, and the central difference.
Sorry, sir. Sorry,
Yes.
sir. Hello.
Ah,
This first term you said it is of second order delta x square. That is slight confusion for me. It is delta x you are written in the denominator. So
in the denominator, it is written to be delta X, but what happens that if I actually write the expression, for example, if I use the Taylor series expansion, then you can see the error which is coming in the Taylor series expansion itself after writing the central difference formula that comes to the order of delta X squared. Let
okay, okay.
me, no, let me write it for you. Give me, for example, this is, hope I have the expression for it. Uh, Let it write it like this. For example, phi j plus 1 is equal to phi j plus d phi dx delta x, and then d square phi dx square delta x square by 2 factorial. Phi j minus 1 is phi j minus d phi dx delta x plus of d square phi dx square delta x square by 2 factorial. Then what I do is basically I subtract both of them, then it becomes phi j plus 1 minus phi j minus 1, okay, divided by 2 equals to d phi dx, so 2 delta x, so d phi dx plus of, it becomes to be, there is another term will come, so will come to be like d phi dx cube delta x cube by 3 factorial, and this is to be like this, x cube by 3 factorial. And then what I do is basically this one is half of d cube dx cube, and then there is delta x square by 3 factorial. Okay, so now d phi dx is phi j plus 1 minus of phi j minus 1 by 2 delta x minus of half of uh, 1 by d cube x dx cube delta x squared by 3 factorial. So this is of the order of delta x squared, and this is called the leading term error or order of accuracy of a discretization scale. Okay, so that's why I wrote it to be like order of delta x squared. Similarly, if I write a formula for that of the forward difference or the backward difference, that will be of the order of delta x. So this term will be of the order of delta x. So that I've done in the previous class itself. The recorded lectures are available in the YouTube, so you can go there and have a look at it. Okay. So
Okay,
going
sir.
with okay, so going with the thing which I was doing. So this one actually comes it to be so Ka T2 minus T1 divided by delta x minus of 2 Ka by delta x T1 minus Ta plus Sd equal to 0. Then this becomes 3Ka by delta x T1 equal to K T2 by delta x plus 2K Ta by delta x plus S dV delta V. So this is the equation for that of the first cell centroid. That is a cell centroid which is present at the right hand side of the rod itself. Okay. Is it clear to all of you?
Okay.
Okay. So now what I have to do is basically I have to derive it for that of the right hand side of the cell centroid itself, the right hand side part. So for that what I have to do is basically I have to draw the control volume. So this one
Sir,
is
is it possible for you to make the screen larger? Is it
uh,
is it possible for you to make the screen larger, the visibility?
yeah, I can zoom up to the extent of. Otherwise, what happens that I have to change slide again and again, and the equations actually becomes difficult for you to trace. So I can make the size to be like this. I think this is better, right?
The largest possible, whatever it is comfortable for you, I request you to do that, so that will be visible for us better, somewhat.
लार्जर तो कर सकते हैं बट इतना ज्यादा लार्ज हो जाएगा तो मेरे लिखने में दिक्कत होगा. 8 सेकंड रुको
Okay,
जरा.
okay,
I think
okay,
this is the best I can do.
okay, sir.
Okay. So then this one actually becomes this 5 actually becomes the fifth cell centered. Okay, this actually looks like this. The right hand side of the right hand most part of the rod itself. Okay, so the proportions are not right. So this is P, this is small e, and this is capital W, this is small w, and this is yeah. Now it is good. So this one is a 4 cell centered, this one is a 5 cell centered. Since I have divided the whole domain into 5 cell centered. So if I go to the equation again, so this actually becomes uh, Ka. So let me write the equations again. Gamma A dt dx small e minus of gamma A dt dx small w plus s delta v equal to 0. Okay. So gamma A T E or TA T or TV you can write. So the rod actually looks like this, and this one is TB and this one is TA. 1, 2, 3, 4, 5. Okay. So gamma A TV minus T5 divided by delta x divided by 2 minus gamma A T5 minus T4 delta x. So T5 is basically the temperature at the P cell centroid and T4 is the temperature at the west cell centroid because the western part of the 5 cell centroid is basically 4. Okay, and B is basically your right hand side boundary, the rightmost boundary of your the domain itself. So 2 gamma A by delta x Tb minus T5 minus of gamma A by delta x T5 minus T4. So which I can write again as there's a source term there. So plus S delta V plus S delta V. Now it will be 3 gamma A by delta x T5 equal to 2 gamma A by delta x Tb plus gamma A by delta x T4 plus S delta x. Okay, so is it clear to all of you?
Yes.
Okay. So now what I will do is basically I will convert this set of equation into matrix form. So this one is the right hand side cell centered, the fifth one. If I go to the previous slide itself, this one is for the first cell centered. Okay. And for a general cell centered, which is basically at the interior of the domain itself, the equation is this one. Okay. So now what I will do is basically I will write the equations for each and every cell centered, and after that I will convert that into a matrix form. So 3k by delta x T1 equals to 2k by delta x Ta plus k by delta x T2 plus s delta v. Yeah. And then this one, the second equation is 2k by delta x T2 k by delta x T1 plus k by delta x T3 plus s delta v. Then 2k by delta x T3 equal to k by delta x T2 plus k by delta x T4 plus s delta v. 2k by delta x T4 k by delta x T3 plus k by delta x T5. Similarly, 3k by delta x T5 is equal to 2k by delta x, sorry, k by delta x T4 plus, so there will be s delta v here, and this one will be 2k by delta x Td plus s delta v. Okay. So is it clear to all of you? So this is for the first cell centroid, this is for second, this is for third, this is for fourth, and this is for fifth. So these three are basically your interior cell centroid. Okay, this one is a leftmost cell centroid, 1, and 5 is basically your rightmost cell centroid. Is it clear to all of you?
Yes, sir.
Okay, so now this equation actually comes to us k by delta x 3 minus 1 0 0 0 minus 1 2 0 0 0 Or should I write it beside so that you can actually compare the coefficients? I have to zoom out a bit, but that is mainly for the uh, hmm, this is 3 minus 1 0 0 0 minus 1 2 0 0 0 0 minus 1 2 minus 1 0. Okay, and this one will be 0 0 minus 1 2 minus 1, and this will be 0 0 0 minus 1 3. Okay, and this will be t1 t2 t3 t4 t5 equals to 2ta plus in the previous class itself I've written that you can express A's delta V as AC plus SPTP. So for the time being we are assuming that your A's delta V is a constant. So if it's a constant and not a linear function of Tp, then AC is basically equal to some value. So I'm writing it as AC itself and SP becomes equal to 0. Okay, so we can write it like this. AC, 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 2TB plus AC, and then uh, this thing should be multiplied by, sorry, K by delta X plus AC, and this thing will be K by delta X plus AC. So is this equation clear to all of you? Hmm?
Yes, sir.
So can we do some, I think you are familiar with MATLAB coding. So I was thinking, yes, that today we can do one coding, which is this heat conduction problem itself. So I want all of you to write this matrix on your copy so that when I actually write the code itself, I can write the code and you can tally that with the coefficients which are present in your copy. So I am giving you a few minutes in order to copy this matrix. Okay, so everybody in the class copy this thing in your copy. Okay, note it down so that I can, because this screen will not be visible when I am coding. So I want you to note it down on your copy. Okay, so is it clear to all of you?
Yes, sir.
Okay, so has everybody noted down? So noted it down. Sweta, Arpan, Dhananjay and
Sir.
Manikandan.
Yes, sir. Noted.
नोटेड ना बाकी लोग नोट कर लिए ना कॉपी में एक बार कंफर्म कर दो तो मैं कोडिंग में जाऊंगा अदरवाइज इट्स डिफिकल्ट फॉर मी टू डू go directly to coding without taking your. I think you can say whether you've noted it down or not.
We have noted down the contents from rectangular block below.
ओके वो मैट्रिक्स नोट कर लिया ना
Uh,
चलो बाकी लोग क्या किए रुको सर बाकी लोग क्या करे देखते हैं श्वेता अर्पण हो गया क्या नोट करना
Yes, sir. Yes, sir.
चलो श्वेता
Yes, sir.
चलो हाँ, इसके बाद मैं ऑक्टेव खोलता हूँ ठीक है यू कैन यूज ऑक्टेव और मैटलैब वॉट एवर यू वांट ओके एज ऑफ नाउ आई एम यूजिंग ऑक्टेव सो कैन यू सी माई स्क्रीन द ऑक्टेव स्क्रीन इटसेल्फ
Yes, sir.
okay so you go to file then you go to new and then you go to new script so these things are pretty much easy okay you can learn octave which is very much similar to that of matlab from the internet okay so Dhananjay, I think you can mute off yeah so what you have to do is basically you have to write the code for the matrix and then you have to solve it for that I'm basically writing the code so I'm writing CLC clear and then close. So CLC actually clears the string and clear actually clears your memory and close is basically if you have any kind of graphical windows which were open previously so it actually closes those graphical windows. Okay. So the problem actually looks like the if I go to the problem itself. So let me show you the problem first. Share screen start. The problem in our case actually looks like so uh, so your domain looks like this. The same thing I've been discussing. So this is TA and this is TV. Okay, so TA and TV are basically the temperature at the left hand side and the right hand side of the domain itself. And we are dividing the whole domain into N control volumes, N or G control volumes. So G is basically your user input. User input. Okay. So what you have to do is basically by using the values at the boundary itself, you actually have to find out that what is the temperature profile inside the domain. So what we will do is basically one is with source term, another one is without source term. So we will see that how it changes. So in case of a source term itself, is TA is greater than TB, the temperature profile looks like a linear one. And if it's with a source term, then it actually looks like this. Okay. So it becomes a parabolic profile. So this is TA, TB, and this one is TA. So TA is greater than TB. So T at any location X, it becomes a function between, it remains between TA, TB, and TA. Whereas this one, for this case itself, uh, when there is a source term, your Tx actually becomes greater than TA and TB both. Okay, is it clear to all of you? That should be the case because if there is a source term, it will receive more heat than that of the temperature will be higher than that of the temperature which is present at the boundaries itself. रॉड का अंदर जो है अंदर टेम्परेचर ज़्यादा होगा compared to that of the temperature which is present at the boundaries because we are using some volumetric source over the whole domain itself. But if it's like a diffusion problem without any source term, so the profile itself will be a linear one. Okay. So is it clear to all of you?
So just one small doubt. In
Okay.
the initially somewhere you mentioned that the west end is 100 and the east end is 500 degrees Celsius.
हाँ, you can. It doesn't. मतलब वो देखो. TA I am taking it to be 500 and this is to be 100. Okay. Then the temperature profile will be like this one. Okay. So if my east
Okay.
face is basically 500 and TA is basically 100, then the slope changes, no? So it looks like this one,
Okay. ठीक है. So you have taken in this case TB, the east end is 100 and west end is
500.
532. Okay. Then understood. And T. Okay, sir.
Okay. So we can take the other case also. So as of now, for the sake of problem itself, I'm taking it to be like 500 to be the west case and 100 to be the east case. And I have to find out the temperature profile over the whole domain. So number of control volumes you have to take inside the domain, that is up to you. So that's an user input. So what we are going to do is basically we are going to create this matrix as I have discussed earlier. Okay. Then this matrix actually comes in the format of x equal to b. So here in your case, x is basically what? T. So T actually becomes what? A inverse B. So this thing you have to use, that you have to do in order to find out the temperature at each and every control volume. So if I know what is the temperature at each and every control volume, I can know the temperature profile. Okay, is it clear to all of you?
Okay, sir.
Yes, sir. I wanted to ask something like which scheme are you going to employ? Like this is a banded system, right? Tri-diagonal system. So are you going to employ Thomas algorithm or some iterative method for this?
We actually use LU decomposition. Uh, okay, this LU decomposition is basically implemented by using ML divide function. So A comma B equals to P. So this thing you have to implement. So by default in the Octave and also in the MATLAB itself, they use LU decomposition in order to find out the value of the T. That is the temperature itself in our case. And for the
Mhm, yes, I mean for
discretization,
small
yeah,
system,
yeah, please.
for so like for small system it's okay, right? LU decomposition, but say if we have large system means many equations, then maybe iterative method has to be employed, right?
That can be done. That I
Uh,
know, that I understand. So then you have to declare the matrix to be a sparse one, and then you can use
yes.
other kind of methods also. But as of now, I'm using this ML divide function since we are taking very less number of control volumes or the cells within that domain itself. Maybe some 5, 10, 15. So it doesn't matter.
Sir, one request, if later on time permits for you in maybe
Ha,
today or
you will.
some other day,
Yeah,
you
yeah, I
can
will do it. I will do it. If it
discuss
permits.
about it. Yes, sir.
Oth- Otherwise, I will share the code with you. If it is not possible in the class itself, I will share the code with you.
Okay, sir. Yes, that
Okay.
is also fine.
So another thing you have also noticed is that what is the order of this matrix? Okay. So this is basically 5 cross 5. So 5 is basically the number of control volumes in my domain. Okay. In my domain. So if there are G control volumes, so it will be like G cross G matrix. So this becomes G cross G. G becomes G cross 1. This becomes G cross 1. Okay. So that's how it works. So while writing the matrix itself or creating the matrix by using the for loop with the program, so you should be careful that how you are generalizing the whole thing. Because for 5 by 5 matrix, it is very much clear. But if it's like a G cross G matrix, then what you have to do is basically write the whole equation in a generalized format. Okay. So I hope I am clear to everyone. Should I go to the problem, writing the program itself?
Okay, sir.
Okay.
Yes, sir.
Uh, so let me share the screen here once again. So let me do it. I think the programming side, yeah, the programming thing is this way. So initially I've written it to be CLC clear and close. So CLC actually clears your string. Clear is basically it clears a memory and closes all the graphical windows that were present initially. So let me save this thing. So in order to save this script, you have to press Control S. So then I can go to my computer and then go to some Ubuntu, and this one is basically some code, write it like this, and then 1D heat conduction plus source. So then what I have to do is basically I have to uh, define the number of control volumes, since this one is basically the user input as said earlier. So you can take it to be 5 number of control volumes or 10 or 15. That's up to you. So, so this one is basically the number of control volumes. Okay. So is it clear to all of you?
Yes, sir.
Yes,
So
sir.
then I have to define delta x. Okay. So delta x is basically the length of the dot. I'm taking it to be zero point 0.5. Okay. So this is zero point 0.5 divided by g. So g is basically the total number of control volumes. Okay. The area I'm going to take it at 0.01 meter square. So this one meter square, cross sectional area in meter square. K is basically zero point 0.5 heat conductivity. So basically your gamma is basically the K in your case. So it will be the heat is heat conductivity, which is basically this one should be a semicolon should be there, a semicolon should be there, and then heat conductivity in watt per meter. And then there is another thing which is V, because since we actually encounter this K by delta x again and again in our matrix itself, so what I'm going to do is basically define a variable like V, so that it is easy for me to write the whole thing. Otherwise, I have to write K by delta x again and again. So is it clear for all up till now? Hello, am I audible?
Yes, sir. What is V, sir? V?
So V is basically a variable I am defining, which is K by delta x. Since if you see the matrix itself, the K by delta x actually appears here and there. Okay. So I want to make the code to be more readable. That's why I'm defining it to be capital V. It has so to make it easier for me to write.
Okay, okay, sir.
Okay. So T1 is basically 500. T2 is 100, and then for I equals to 2 is to 1 is to G minus 1. So what I'm doing is that you will see from the second row of the matrix itself, there is a pattern. So 2 actually comes in the middle and minus 1 actually comes on both sides. Okay. So have you seen the pattern there? So 2 actually comes in the middle, minus 1 comes on both sides. So let me show you the matrix again. So can you see the matrix now?
Yes, sir.
So there is minus 1 on both sides and 2 in the middle. Okay. Okay. So what I will do is basically I will write a for loop so that it actually feeds the matrix from the second row to G minus 1th row using these values by the values 2, minus 1 and minus 1. So another pattern you will see is that in the second uh, part itself, or in the second row itself, 2 actually comes at an index of 2. Okay. Then it actually shifts right when it goes to the third row, and it then shifts right when it goes to the fourth row. Okay. So this thing should be included when you are writing the for loop. Okay. So is it clear to all of you?
Yes.
Okay. तो इसके बाद में इसको शेयर so what you have to do is basically I have to use a counter which is j, which is basically 2 plus n, and j equals to 2 plus n, so m is equal to 0, that I have to write. So m equals to 0, j equals to 2, so I is basically your row and j is basically your column. So since 2 is basically in the second column itself for the second row, so that's why it is 2 plus n. Okay, so it's being shifted. So that's why I'm writing it like this. So now A is a matrix. So A is I comma j minus 1 equals to minus of B, and A I comma j plus 1 equals to 2B. Sorry, minus B, and then A I comma j 2 into B. Okay. So m equals to n plus 1. Okay. So is it clear to all of you?
So, but how will you like add the elements of the first row? This
हाँ
is
वो
from second row, right?
हाँ मैं मैनुअली कर दूंगा ना. अभी के लिए पैटर्न में बना रहा हूँ, ठीक है. फर्स्ट और लास्ट रो के लिए
Okay.
मैं मैनुअली करूंगा. अभी के लिए मैं सेकंड से शुरू करके जी माइनस 1 तक जा रहा हूँ.
What is
फर्स्ट.
this? Yes, sir. Yes.
हाँ विच वन. जे तुम्हारा
Yes. Yes.
देखो ना
Yes.
जे.
Yes.
विच वन. दिस वन जे जे.
No, sir. The A of I comma j minus one. A. What is?
हाँ, A is basically your coefficient matrix on the left hand side of the equation itself because it comes in the format of Ax equal to B. I is basically your row index and J is basically your column index. Okay. So for
Sir,
example,
sir, your program contents are very fine. It is difficult to read.
difficult to
Can you
read ना.
enlarge it
अब ठीक है ना.
little bit? Now it is better.
Now it is better ना. अब बेसिकली क्या होता है, I actually ranges from G2 to G minus 1, मतलब सेकेंड रो से शुरू हुआ G minus 1 तक गया, ठीक है. एंड इट एक्चुअली 1 मतलब क्या होता है, पहले 2 वैल्यू लिया उसके बाद 3 लिया, ऐसा करके G minus 1 तक गया, ठीक है. J इज बेसिकली 2 प्लस n, n का वैल्यू मैंने 0 पकड़ लिया, ठीक है. तो J इज बेसिकली योर सेकेंड कॉलम. ओके, सिंस I is basically your row index and J is the column index. A is your coefficient matrix, the matrix on the left hand side of the equation. So ai comma j minus 1 is minus b, ai comma j plus 1 is minus b, and ai comma j, which is basically your value at the middle, it is actually 2 into v. V is what? K by delta x. Then what I do is actually I change m is equal to n plus 1. M equals to n plus 1. Why? Because your actually two value shifts to the right when you actually go to the second row. Okay. So now 2 value actually comes at what? 2 into v. It comes at j equals to 3 in the third row. Okay. So that's why I have to change it. I have to shift it. So that's why n equals to n plus 1. Is it clear to all of you? Arpan, Manikandan, huh? Manikandan, huh? Dhananjay. Is it clear to all of you?
Yes, sir.
Yes. Yes.
हाँ, बोलो नहीं तो मुझे समझ नहीं आता है ना. यू रेस्पॉन्ड. इसके बाद जैसा अड़पन ने बोला था, मुझे फर्स्ट रो का जो एलिमेंट है वो डालना पड़ेगा. सो दिस इज इक्वल टू 3 into v. ओके. सो a of 1 comma 2 इज बेसिकली इक्वल टू माइनस ऑफ वी हो गया, इसके बाद ए और जी कॉमा माइनस वी हो गया, एंड देन ए ऑफ जी कॉमा जी इक्वल्स टू 3 into v हो गया. Is it clear to all of you?
So I want to ask one thing, like
हाँ
in the for loop, sir, for j index, can we use another for loop if we want to?
घुमा के लिख सकते हो,
Like
but I think this one is a simple one. Okay.
yes, I just asked, sir. I mean,
हाँ
if
कर
we
सकते
want.
हो, देखो प्रोग्राम तुम 10 तरीके से लिख सकते हो, ठीक है, मैं ऐसा लिख रहा
Mhm.
हूँ कि तुम्हें आसानी से समझ में
Yes, sir, yes, yes.
आए. इसके बाद मैं डिस्प्ले करूंगा, ठीक है, फॉर एग्जांपल 5 रीड पॉइंट्स है, तो इसके लिए मेरा एक सेकंड तुम्हें दिखाता है मेरा मैट्रिक्स कैसा है. डिस्प्ले करूंगा दिस वन, put a space here, I think that one is better. So now it actually 5. So this is your matrix, by the way. So k by delta x is coming to be like, let me, k by delta x is coming to be what? Display v. So this is coming to be, k by delta x is basically 0.05. So 0.05, which is multiplied by 3 itself, it comes to be 0.15. And this one is 2 minus 1 and minus 1. So it is coming to be minus 0.05, 1 and minus 0.05. Okay, that's how the whole thing appears. So you can tally with the, otherwise if I actually take v to be 1, you can also see, let me, so if I take v to be 1, you will basically get the coefficient matrix. So is the matrix seems to be right as I have written in the copy itself. Arpan, Manikandan, Dhananjay.
Yes, sir. Same.
ओके, तो v का वैल्यू बैठा दूँ तो वो अलग हो जाएगा, v फैक्टर से मल्टीप्लाई हो जाएगा, तो नाउ इट लुक्स लाइक दिस. ओके, इसके बाद मुझे क्या करना पड़ेगा, मुझे ए मैट्रिक्स मिल गया, इसके बाद मुझे क्या करना पड़ेगा, मुझे एक्स मैट्रिक्स बनाना पड़ेगा, विच इज योर डिस्टेंस एरे, बिकॉज तुम्हें प्लॉट करना पड़ेगा ना, मैट्रिक्स नहीं, बेसिकली एरे बनाना पड़ेगा. तो x1 is 0, x2 is your x1 plus delta x into 0.5. ओके, तो फर्स्ट वाला जो पॉइंट होगा वो 0 पॉइंट में होगा, तो एट x1 equal to 0, that is basically t है. At x2, the value of x at 2 is basically x1 plus delta x multiplied by 0.5. Since the distance of the cell centroid from that of the boundary patch is basically zero point 0.5 into delta x, that is half of delta x. Is it clear to all of you?
Yes, sir.
इसके बाद अंदर का जो डेल्टा एक्स रहेगा, मतलब एक्स का जो एरे रहेगा, आई विल राइट इट लाइक 3:1 1:2 g plus 1 and xi equals to xi minus 1 plus, ओके, इसके बाद इसे इंट करना पड़ेगा, इसके बाद x g plus 2 equals to x g plus 1 plus delta x into, okay. So for example, if I'm actually displaying this, so the number actually goes to g plus 2 since there are g cell centroid. So we have the coordinate for the g cell centroid, and there is plus 2 since we want to take the location of the east face and the west face also. Okay, which is x equal to 0 and x equal to 1. So therefore, if I actually display x, so now it comes to be like, so this one is over. So this one is your x. Okay, so this is 0, 0.05, 0.15, 0.25, 0.35, 0.45, and zero point 0.5. And as I've said earlier, zero point 0.5 is basically the length of the whole plot, okay, that I've taken to be zero point 0.5. So is it clear to all of you? हेलो मैं
Yes, sir.
ऑडियो हाँ मतलब समझ में आ रहा है ना मैं जैसे बता रहा हूँ हेलो
Yes, sir. Got it.
गॉट इट ना आई थिंक श्वेता also other people left the chat window.
Yes, sir.
Okay, so you got it right. So then what I have to do is basically your b is zeros and then g comma 1. Since g is basically b is what? B is a column matrix which has a dimension of g cross 1 that I've said earlier. So P1 comma 1 is basically your 2 into P1 into V plus is sorry P1 into V and P for I equals to 2 is to 1 is 2 G minus 1 equals to AC and B G comma 1 which is basically your last row. So this is basically 2 into P2 into V. So is it clear to all of you? B जो
Yes, sir.
सोर्स मैट्रिक्स था
Yes,
डायग्राम
sir.
वो मैंने फिल किया तो पहले वाला टर्म था 2 into T1 into V. T1 is the temperature at the waste surface and Pi comma 1 is basically your this will be 0 since there is no source term तो बीच वाला 0 हो जाएगा which actually ranges from 2 to G minus 1 तो उसके बाद क्या होगा G comma 1 जो है जो लास्ट वाला जो टर्म होगा रो में कॉलम मैट्रिक्स में जो लास्ट रो में होगा that is 2 into T2 into V. Okay, so now I have to use this ML divide. So ML divide A comma B. So A comma B is basically A inverse B. So what I'm doing is basically I'm dividing B by A. So that is A inverse B itself. And then display T. So let us see whether I get a temperature distribution or not. So now I go here. Yes, I get a temperature distribution. So 460, 380, 300, 220, and 140. So these are basically the temperature at the interior cell centroids along with the boundary cell centroid also. But here we have not included the temperature at the patch also. So which we have to do it. So is it clear up till now? अर्पण
Yes, sir.
ठीक है समझ में आ गया ना तो इसके बाद क्या करना पड़ेगा मुझे फॉर एग्जांपल इफ आई वांट टू दिस X array that I've done so I want to display this X array also so let us show you that this one is your X array okay so if I want to plot this X versus T so there will be an error since the number of elements which are present here for example the temperature is 1 2 3 4 5 so 5 temperatures are there but the X also include the left hand side patch location and also the right hand side patch location so there are 7 points 1 2 3 4 5 6 7 Is it clear to all of you?
Yes, sir.
मतलब यहाँ पर मैं प्रिंट करने जाऊँ तो वो बोलेगा यहाँ पर एरर है, बिकॉज दोनों एरे का वेक्टर लेंथ अलग है ना, द वेक्टर लेंथ मस्ट मैच। तो वेक्टर लेंथ करने के लिए जो टी जो एरे है मेरे पास, उसमें मुझे जो बाउंड्री का टेम्परेचर है वो इंक्लूड करना पड़ेगा। ओके, so then I have to define another thing which is called T mod. Okay, so T mod is basically equal to zeros G plus 2 comma 1. Okay, so now why G plus 2 comma 1? So the matrix dimension is G plus 2 comma 1, since temperature itself is a column matrix, and zeros is basically I am taking all the matrix element to be 0. So it's a null matrix of the dimension G plus 2 comma 1. Okay, so T mod 1 comma 1 is equal to T1, and T mod G plus 2 comma 1 equals to T2. Okay, and then I write a for loop. So for loop is basically 2 is to 1 is to G plus 1. So int and T mod comma 1 equals to T I minus 1 1. Okay, so what it does is basically it actually, for example, if I display T mod, okay, so you will see that your T mod looks like, move it a bit, otherwise it will not work. Your T mod, uh, let me remove this comment, otherwise you will get error. So your T mod is basically 500 on the left hand side and 100 on the right hand side itself. So the temperature at the interior, the control volumes itself is basically 0. So what I have to do is basically I have to put the temperature that I have calculated by using ML divide into the array itself, which I am going to plot. So T mod I plus 1 is basically T I minus 1 comma 1. Since I have to shift the first temperature to a second one, the temperature at the first address to the second one, and I have to take the first address temperature to be the temperature at the left hand side most part of the rod itself, which is 500. Okay, so is it clear to all of you? And then I have to
Sir,
plot.
means we have to add the new temperatures, right?
बेसिकली
In
एरे में
this.
न्यू टेम्परेचर ऐड करना पड़ेगा, एरे को सामने एक एड्रेस तक शिफ्ट करना पड़ेगा, बिकॉज लेफ्ट हैंड साइड में तुम्हें एक न्यू टेम्परेचर लगाना पड़ेगा ना, ठीक है?
Yes, sir.
ओके, सो नाउ आई प्लॉट x comma t mod. So let us see that. So now I get a linear profile, right? So that's the profile that is of the temperature in a purely conducting rock. Okay, so this is only conduction which is happening here. So is it clear to all of you?
Yes, sir.
Okay, कोई भी स्टेप समझ नहीं आ रहा है मुझे बता देना, मैं एक्सप्लेन कर दूंगा फिर से, ठीक है? ऐसा कोई बात नहीं, तो डू इट फॉर द फर्स्ट टाइम. सो नाउ व्हाट आई विल डू इज बेसिकली आई विल ऐड अ सोर्स टर्म. अब सोर्स टर्म कहाँ पर होगा ऐड, वो तो मैट्रिक्स में आपको पता है, ठीक है? तो व्हाट आई विल डू इज एट द सोर्स टर्म. सो हाउ टू डिफाइन द सोर्स टर्म, दैट्स अ क्वेश्चन. So source term is basically equal to this AC is equal to Q into delta X, delta X equal to Q into delta into dA into area. So Q is basically equal to some, uh, let us take it to be 1000, which is the dimension being watt per meter cube. Okay, so that's how it works. AC is equal to what? A is delta V. So this is to be S. Let us write it to be S for your own ease. So this one is delta X. So I can write it to like delta V is equal to delta X into area. So this one is basically delta V. Okay. So AC equal to S delta V. Okay. Is it clear to all of you?
Yes, sir.
Okay. So now what I have to do is basically I have to add this source term in the matrix itself.
B
So
matrix.
yeah, the B matrix. Good. So what I have to do is basically to go here, and then this will be equal to AC, and this should be AC. So I hope the AC I define it to be right. Okay. So let us take it to be like 5. So now it becomes a parabolic one, but the heat source itself is low. So I can make it to be low. So now it becomes, so you can see with much higher heat source. So this one is TA, this one is TB, and this one is the temperature at the interior of the rod itself. Okay, the part that we have considered in our case. Is it clear to both of you?
Yes, sir.
Okay. Is it clear to Arpan?
Sir, can you repeat once again, sir? And the code part, sir,
फोर्थ
where
पार्ट
you
में जो
are.
बी मैट्रिक्स था वहां पर मैंने सोर्स ऐड कर लिया ठीक है so what I added was actually is delta v okay so is delta v
Actually, because yes,
is delta v is basically AC ना तो बी जो सोर्स मैट्रिक्स में है वहां पर ही सोर्स ऐड होगा तो B11 में AC ऐड होगा BI1 में AC ऐड होगा और BG1 में AC ऐड होगा ठीक है तीनों जगह मैंने AC ऐड कर ली और AC मैंने कैसे डिफाइन किया AC is basically S into delta V. So delta V is what? Delta A into A, delta X into A. So S delta V is basically AC. मैट्रिक्स में देखो वही लिखा हुआ है तो मैंने एस डेल्टा
yes, sir.
वी ऐड किया उसके बाद मैंने फिर से प्लॉट किया ठीक है प्लॉट करने के
Yes,
बाद
sir.
देखोगे यहाँ पर 500 डिग्री टेम्परेचर है यहाँ पर 100 डिग्री टेम्परेचर है बीच में जो टेम्परेचर है वो दोनों टेम्परेचर से ज़्यादा है ओके सो नाउ इफ आई रिड्यूस अ हीट सोर्स फॉर एग्जांपल इफ आई make it to be like some 1000 so what happens that it comes to be a slightly parabolic one since there is a source term but it is the temperature is between 500 and 100 itself okay so that's what I'm saying so with the introduction of that if I introduce source term inside the domain itself the temperature profile becomes to be a parabolic one so is it clear to all of you
Yes, sir.
Yes,
well,
sir.
okay so that's how it works okay so this code I will share with you by the way so I can also I hope I can paste it here also. So in the chat box I can paste it. Chat box. So I think there is a flash for that. Oh, yeah. The second one is the right one. The first one is not the right one since there is a slash. इसको मैं delete कर देता हूँ. हाँ. So the code has been shared. Okay. So you can see the code itself. So you can directly put it in the octave and then you can run it. Okay. Is it clear to both of you?
Yes, sir.
Yes, sir.
So that's how it works. So this is basically how you can basically find out the temperature profile inside the rod itself by using the central difference scheme. So the coefficients will basically change the value of the this A matrix itself. The coefficient will change when I actually change the discretization scheme. I hope you understand this. Uh, so in the subsequent class also I will make you understand that how to code in a way so that I can change the schemes in a what should I say in a convenient manner. Okay, so the coefficient itself will change. For example, if I write it will be like AP phi P equals to AE phi E plus AW phi W plus source. Okay, then this AP is what 2K by delta X, A is what K by delta X, AW is what K by delta X, and there is a source term which is present there, which is basically your base delta V or AC, whatever you call it to be, if it's a constant source. And AP is basically what? AE plus AW. Okay. So what happens is that if I actually, you will see that if I change the discretization scheme, this AP, AE and AW will change. Okay. So what I will do is basically, if central difference, my AP, AE and AW will be some value. If a point, else if a point, your AP, AE and AW will be another value, and so on. Okay. So that's how you can write the program in a modular manner, and then you can basically use it to create your COD solver. Is it clear to all of you?
Yes, sir.
ओके, तो मतलब सोचना सीखो कि कैसे करके तुम उसे लिख सकते हो. ओके, इट इज प्रीटी मच important to understand these things. So as we have actually learned the discretization scheme, so another thing which is very much important is that there are three terms that you should remember by heart. So one is basically boundedness, another one is accuracy, another one is transport limits. Okay, so what do you mean by boundedness? So for example, there is a temperature profile inside the rod itself. So this one is TA and this one is TV. Okay, so T is greater than TV for my case. So the temperature which is present inside the rod, so T as a function of X actually lies between TV and TA. So this is basically called boundedness. Okay, so what do you mean by the word unbounded? So if the temperature inside the rod itself is higher than the temperature which is the temperature inside the rod is higher than TA and TB. So that is basically called unbounded problem. So typically in an unbounded problem, sometimes the problem becomes unstable or it doesn't converge. Okay, the temperature, the heat source is very much high. Sometimes it may happen that it doesn't converge for a complex flow problem. So these things should be kept in mind. So when it's a unbounded problem, you should be cautious about the convergence of that problem. So this one is called the unbounded problem. And the first one is a bounded problem. Is it clear to all of you?
Yes, sir.
Okay. So there is another term which is called the accuracy. Okay. So is it recording or not? Yes, it's recording. So there is another thing which is called the accuracy. So what do you mean by the accuracy of a discretization scheme? Of a discretization scheme. So accuracy means,
Uh,
yes, do you have any question?
No, sir. No, sir. No
Okay.
question.
So the temperature or any variable predicted by numerical methods or numerical discretization should agree closely with analytical or experimental data. For example, for our case itself, we can see that if it's a purely diffusive case, so k tail square dx squared equal to 0. So if I actually write it to be like dt dx, so this one is a constant. So temperature then becomes C1 x by L plus C2. We know the boundary condition. So x equal to 0 is TA and x equal to L is TB. So this one is a rod and this one is x equal to 0 and this one is x equal to L and this one is TA and this one is TB. So then TA is basically equal to C1 plus C2 and TB is basically equal to C2. So C1 is basically TA minus TB. Okay. So T is basically equal to TA minus TB x by L plus TB, or it can be written like TA x by L plus TB 1 minus x by L. So then what you have to do is that for a very simple case, you know the analytical solution. So you will find the temperature which is predicted by the analytical solution along the length of the rod itself, and then you will compare it with your the data you are getting from the numerical one. So if I actually take the temperature profile, for example, uh, let me see the temperature profile here. So, let me do it for you. So for example, there are some like 5 points. So the temperature profile, uh, let me consider the source temperature. So the temperature in the middle actually comes out to be like 300. So this is 300 your temperature at the middle. So if I show you the screen again, so for a purely conductive case itself, the temperature in the middle actually comes out to be 300. So can you see my screen? So if I
Yes,
actually
sir.
let me print T mod, so you will understand. So display uh, T and then this will come as 5. So you can see what is the temperature in the middle. That is coming to 300. Okay, 500, 460, 380. Three temperature on one side. From another side, this is 220, 140, and 100. So in the middle, it is coming to 300. So if I actually go to the analytical solution also, so let me share my writing screen. So if I go to the analytical solution also, we will see that my temperature in the middle. So at x equal to 0.5 divided by 2 or TL by 2, that is coming to be TA by 2 plus TB by 2 or TA plus TB by 2. So it is actually 500 plus 100 divided by 2, which is coming to be 300. Okay. So now we can see that the solution is going to be accurate form. So what we did was actually we tallied the analytical solution with the numerical form. Is it clear to all of you?
Yeah, so the
Yes.
difference between the two is the accuracy, right?
The difference between
I
the two
mean,
is accuracy. So
yeah.
another thing is basically, Sweta, you are going to ask something. You ask, and I will explain another form of accuracy. Sweta, do you have any question? So difference between the two is the format of accuracy. So another format of accuracy is that another format of accuracy is truncation error. So I hope Arpan, you remember that what do you mean by truncation error? So phi j plus 1 is basically equal to phi j, and then this d phi dx and this delta x plus d square phi dx square delta x square by 2 factorial and so on. So these errors are basically called the truncation errors. For example, if I want to find out the phi j plus 1 from phi j itself. So this truncation error, you have to you have to identify and calculate and reduce and minimize uh, and minimize. So how do you reduce a truncation error, Arpan?
So by reducing the grid size.
Yes, accurate. That's correct. So if I reduce delta x, the truncation error actually reduces. So if it's a higher order scheme, it reduces very quickly. If it's a lower order scheme, it will reduce at a lower pace. Okay, and that's why we actually go for higher order scheme. But that's not the case always, because sometimes this higher order scheme also gives rise to something which is called numerical oscillation. So unphysical kind of thing you will see. Or sometimes, for example, there is one thing which is called numerical diffusion or false diffusion. Those kind of things you will see in the uppoint scheme. So it's not always the case that we should go with a higher order scheme. But as a general rule of thumb, we go for it because that reduces your truncation error. Okay. So there is another thing which is called transportiveness. So what do you mean by transportiveness? Transportiveness. So for example, there is a uh, thing like AP phi P equals to E phi E plus AW phi W. Okay. So and the flow is basically happening from west to east. Okay. From west to east direction, that is from left to right. Then the your phi P actually becomes A by AP phi E plus AW by AP phi W. Since the flow actually happens from west to east, ideally AW by AP should be greater than AE by AP. If the flow happens from east to west, then AE by AP becomes greater than AW by P. Okay, is it clear to all of you? That is called transport unions.
Similar to upwinding, right? Something
Yeah,
like
yeah, yes,
upwind.
yeah. But in the case of we actually introduced uh, transport unions here, the main problem in the convection scheme. So if it's a convection diffusion problem while upwinding, we introduce transport unions there. But the problem is that that introduces numerical diffusion. So that you will see. So there is another thing which is called conservativeness. So the from the word itself, you understand that there is something which is becoming conserved. So for example, there is a plane like this, or there's a control volume like this. If it's a control volume in 3D, this one is X, this one is Y, and this one is Z, or this one is Y, and this one is Z. So if the flow is basically happening from left to right across this plane itself, that is your west phase, then phi of capital W is basically equal to phi of, your mass at capital W, mass squared at small w, this should be equal to that of mass at small w minus is equal to mass squared at plus. So W plus actually means at the right hand side of the face itself, and W minus actually means the left hand side of the face. So the mass which is entering per unit time from the left hand side of the face is basically same as a mass which is leaving the left hand side of the face at time t, per unit time at time t. So is it clear to all of you? So the mass is remaining conserved. The thing which is going in should come out. Okay. Is it clear to all of you?
Yes, sir.
Yes, sir.
Okay. So this is basically called conservativeness. For example, there is a problem like this. There is a domain like this, and it is filled with some water. Okay. Or and then you are injecting gas, and then this one is outlet, and this one is an inlet. Okay. So the gas which is coming through the outlet inlet should be equal to the gas which is going out of the outlet. Otherwise, mass conservation is violated if they are not same, and this introduces numerical error. Is it clear to all of you?
Yes, sir.
So I'm giving you 5 minutes break, and then I will introduce the uppoint scheme, and then we will close the class. Okay. So wait for yeah, a 10-minute break I'm giving, and then I will start the uppoint scheme. Okay. So I will request both of you to wait for 10 minutes. Okay. Is it okay with you? Urban Sweta, is it okay for you for to take a break for 10 minutes?
Okay, sir.
Yes, sir.
As per your convenience. Yes, sir.
हाँ 10 मिनट के लिए थोड़ा सा बैठ जाओ जो सिखा है वो एक बार देख लो उसके बाद मैं अपॉइंट स्कीम चालू करता हूँ वो थोड़ा सा अलग है तो मैं थोड़ा सा टाइम लेके करना चाहता हूँ इट विल टेक अबाउट सम 10-15 मिनट्स फ्रॉम देयर उसके बाद मैं अगले क्लास में एक प्रॉब्लम सॉल्व कराऊंगा अपॉइंट स्कीम यूज करके ठीक है कोडिंग करके चलो ठीक है मैं 10 मिनट बाद आता हूँ Hello, am I audible?
Yes, sir.
Okay, let's wait for Arpan and then I will introduce our point scheme too. So, do you have any
Sir,
problem regarding the way I teach, or is the tempo okay, or the way I make you understand is okay for you?
sir, I understand that.
You understood it, right? Because these things are pretty much difficult. Though I want to make you understand, but if you don't do it by yourself, you will not get the essence of it. So,
Okay, sir.
point scheme. So I think we should start. Arpan will join in a meantime. So what is our point scheme? Okay. So in the previous class itself, I derived that Fe phi minus Fw phi W is basically equal to gamma E d phi dx at E minus of gamma W d phi dx at W. Okay. So Fe is basically your rho UE, and this actually comes from the general transfer equation. So if you are unable to get hold of it, I will derive it for you. So d rho U dt plus, sorry, rho phi plus del dot rho U phi minus of grad T, sorry, uh, gamma del square phi plus EC plus system. Okay. So if that's a convection diffusion problem without any source term, so this term becomes zero. This term also becomes zero since this one is a steady convection diffusion problem without any source term. mm, Source term. Okay. So now this equation, what I have to do is basically I have to use a Gauss divergence theorem. So first I have to do the volume integral, so which is basically del dot grad phi dv. So I have to convert this into a surface integral, which is grad phi dx. Sorry, this is basically rho u phi dA, or you can write it to like n cap dot dA, and this is equal to n cap dot uh, gamma grad phi dA. Okay. So n cap is basically the normal vector at the surface itself. So now this actually becomes this one, since we know that rho u is basically equal to small capital A. So which has a subscript of small a, which if it is calculated at the east face, and small w if it is calculated at the west face. So the equation actually becomes Ep phi equals minus Fw phi W equals to gamma d phi dx east minus of gamma d phi dx W. Okay. So is it clear to you, Sweta?
Yes, sir.
Okay. So now what you have to do is basically you have to use a affine scheme. So in case of affine scheme itself, the right hand side is basically your central difference formula, and the left hand side is basically your affine scheme. So this scheme actually depends upon the directionality of the flow. So this is the uniqueness of this scheme. So for example, if the scheme actually the flow happens from west to east, and this one is a p cell centered, and this is small e, this is capital E, and this is small w, and this is capital W. So if the flow is happening from west to east, then what happens is that uh, phi E becomes equal to phi P, and this gets projected to this, and phi W is basically equal to small w. Okay, so if my equation actually looks like if phi E minus if W phi W equals to gamma d phi dx at east minus of gamma d phi dx at W. So this one is basically equal to if E phi P if E phi P minus of if W phi capital W. So it changes from small w to capital W. It was small w since this is calculated at surface.
Sir, this is both are the small W's.
Yeah, both are small w's. So this was small, this is also small, but this is capital P and this is capital W.
Yes, sir.
And this is equal to gamma phi east minus phi P divided by delta x minus of gamma phi P minus phi W divided by delta. Fe and Fw we already know, since in the problem itself uh, u is given and density itself is given. So since we are solving only one equation, the velocity I don't want you to find it out from the continuity and the momentum equation. U value I will give you, for example, 1 meter per second. Rho is basically the property of the fluid itself that I also will give. So what remains is that, so this can be written as capital F. So because Fe Fw equal to capital F because of conservativeness itself. So F phi P minus F phi W equals to gamma phi E minus phi P divided by delta x minus of gamma phi P minus phi W divided by delta x. So is it clear to you?
Yes, sir.
So now if the flow changes, if the directionality changes, so it happens from west to east itself. So now it becomes phi small w equals to phi P and phi small e equals to phi capital E. Okay, so that's how it changes. So if it actually becomes uh, so phi E, it becomes phi capital E. So it becomes if E phi capital E minus of if W phi capital P equals to the same thing, which is gamma phi e minus phi e divided by delta x minus of gamma phi p minus phi w divided by delta x. Is it clear to all of you?
Yes, sir.
तो डायरेक्शनलिटी के ऊपर डिपेंड करता है कि तुम्हारा कोएफिशिएंट क्या होगा, ठीक है. So in the next class itself, I will discuss it in great detail. I think that's already 2 hours. I think anything in Excel will not. Uh, I don't think you will remember that thing. So it's better that we start in the next class afresh. That what are the problems we face in the offense. Okay.
Okay, sir. Okay, sir. But sir, इसकी recording and the
हाँ
lectures prepared
मैं
is
तो अपलोड कर देता हूँ ना यूट्यूब में.
okay, sir. Okay, sir. Thank you, sir.
हाँ ठीक है, मैं अभी अपलोड में बैठा देता हूँ, कोई दिक्कत नहीं है, मैं लिंक शेयर कर दूंगा पूरा.
Okay, sir.
ओके, ठीक है, बाय.
Thank you, sir.
ओके.